Hey guys, here's the video to help you with some of those volume problems where you're revolving around something other than one of the axes. I think in class we did the x-axis, we did the y-axis, but what I wanted to do is I wanted to revolve around something like like y equals 2. So we're going to revolve around y equals 2. Okay, so let's see if that's I used the same one from class, by the way. This is y equals x squared. So this would be 1, right? 1, 1. So I want to go 2. So let's go up here. Something like this. So here is the line we're revolving around. Okay, let me sneak that down a little bit more. There we go. All right, so when I revolve this, there's going to be some, clearly there's going to be some space in between because of all this empty space. So our region is here. This is our region. And let's see if I do this right. I got something like here, and then maybe like that. If I just do that part, I know I made it a little bigger, but that's the idea. So I have all this volume that's being generated in between as this gets revolved around. Okay, so if I draw one disk that sort of connects them, let's see if I can make this look okay. There's the first disk, right? And here's the radius of that disk. And the second disk would be here. Okay. And the radius would be just this part. I'll draw it really close, right to there. So I have a big outer sort of ring, and then sort of kind of an inner ring. Okay, so you only really need to draw one of these, but if it helps you to draw like a couple of them so you can really get a good visual, that's fine. But it's really no different than any of the other ones we've done, except for the fact that now there's this space in between where the radius is going to be a little harder to actually figure out. Normally we were just connecting the axis of revolution to the curve, and we're like, oh, it's just that height, or sorry, the radius, right? Just this value was the radius, or this value was the radius. And even if we went this way, it was still connected. It would just be the function itself. But here it's a little different. This right here is 2. So this distance all the way down is 2. But my big R is not quite all the way down, right? The big R goes from the axis of revolution to my, actually, sorry, the big R is down here, to the curve, right? The black radius here. So this distance would be a full 2 minus whatever this is. Okay, so I'd have to subtract that little piece out. Well, that little piece is, in this case, x squared. So my big R is going to be 2 minus x squared. Again, the 2 comes from, because that's just the value of, from the axis to the revolving axis, right, from the original x-axis to the revolving axis. And then we have to take out this part here to represent from the center of the disk all the way to the outer edge of the disk. Okay, so that's the big radius. The little radius would be the same kind. Sorry. The little radius would be basically the same thing. It'd be the full 2 minus all of this now. That's what we'd have to get rid of. Well, this distance from the axis to this point right here would be the value at y equals x. So that would be 2 minus x. So it's a little tricky. It's not just the function. You have to really think about what value represents this length all the way to here. What value represents this length all the way to here. Okay? And it's essentially still top minus bottom if you think about it, because the top one is the x squared and the bottom one is the x if you think of it that way. But I don't usually go, to come up with the value all the way up here seems kind of silly. You can still get the value very easily using the original functions and using the value of the axis of revolution. Okay, so my integral would be the same idea. It's still 0 to 1, none of that changes. It's still pi r squared, but it's essentially this, which is exactly what we had in class. The only difference is finding big R and little r had a little bit of a twist. Okay, so this would be pi from 0 to 1, 2 minus x squared squared minus 2 minus x squared. And that would be dx. Okay. Now I'm not going to bother actually solving it because at this point I don't think there's an issue. I think the issue is going to be right here. That's going to be the hardest part. is looking at a picture like this and being able to determine the radius when you have some axis of revolution that's not one of the normal coordinate axes. Okay, so try the couple that that you have left from the homework on this with this idea and see how it goes. If you still need help, I can always make another video. All right, this is your example for doing one with a horizontal. Now I'm going to do one with a vertical. Okay. All right, let's use the same functions. So we had y equals x. I'll do it here. Y equals x. Y equals x squared. But this time we're going to go around the line x equals -1. Okay, so -1 would be here. I'm revolving around this line. So this region is going this way now. Okay, it's revolving around that line. So if I draw this reflection properly, it's going to be something like this, give or take, maybe with a little bit of that. That's not too bad, actually. That actually came out okay. So this, if I revolve it around, I'm going to have a disk, and I'll just draw a sample disk sort of in the middle. And this one's going to go horizontally. And the radius is going to go all the way to here. Okay, and I guess in the other one I didn't actually draw the thickness of the disk, but remember, that's just the dx part. It's not that big a deal. Okay, but this, if you just think about what the cross section would look like, it helps. And then the inner disk would be here. Oops. Something like that. And I'll just draw it a little bit off to the side, not to the side, but just below it so you can see it. And it'd be basically the same idea. Okay, so you have the outer radius, which is here. That's going to be your big R. And of course our little radius is from the axis of revolution. This is x equals -1 all the way to the left curve. So that's a little r. So I need to figure out the length from here to here. Well, I know that this curve is x squared. That's great. If I plug in x, I get y. But I don't want to do it that way because I'm going basically horizontally. So I need to figure out what this is in terms of y so I can figure out what this length is at any time. Okay, so this is going to be x equals the square root of y. Now I know there's plus or minus, but we're only using this half. So we're only using the positive half. The negative half would have been over here. Okay, so you just got to look at the context of the problem you're doing and use the appropriate part. So x equals radical y is this length. I'm sorry, from here all the way to here. But there's another extra little bit of space, right? This little bit of space is just 1 unit. This is radical y, and this is 1. So I have a big R of 1 plus the square root of y. Okay, you could also think of it in the other way around if you want. If you're thinking like area between curves kind of a thing, you could do square root of y minus a -1, and that'd be the same thing. Okay, so again, just to repeat, I want to focus on big R, which is the distance from the axis of revolution to the rightmost curve. Okay, so from here to the axis is 1. From the axis to the actual curve is radical y. Okay, because we're doing it in terms of y since we're going this way. So little r then, I'd still have the same 1 over here. So from here to here gets me back to basically, this is basically like your starting value. If you think about it, if you've already done the problems where you do the y-axis, you're starting from here and you're just figuring out the actual equation. So all you're doing here is you're just adding 1. Or if it was on the other side, we'd just be subtracting 1, kind of like the other one, the one we just did. So 1 plus and then the distance from here to here, well, this one's convenient. It's really the same thing. That's y. So this is going to be 1 plus y. All right, so if I go to set up my integral, it just so happens it's also from 0 to 1, right? Because I'm using the y values now, which happen to be 0, and this crosses at 1. Just be careful. I think we did one in class where it went up to like 8 or something. You're using the y values because you're making all these disks horizontally and you're accumulating them as you move your way up. Okay, so I need to use y values. Start at 0, go up a little bit, all the y values until eventually we're done. All right, so it's going to be pi big R squared minus little r squared and dy this time, and there's your setup for your integral. Okay, so it's a little bit of an extension on the ones we did together, but hopefully not too bad. Try to really focus on getting a good picture. Draw your curve nicely. Let the calculator get you the curve if you're having trouble visualizing. But draw it by hand so that you can draw in one of these discs. Because as soon as you draw in these discs, you can draw in the radius and really focus on, okay, how do I get this piece? How do I get that piece? And as soon as you get these, I'm telling you, these are the hardest part. Once you get these, the rest is automatic. This just put in the calculator. Okay, I mean, this one you technically could do by hand, but who would want to? Okay, so do this one in the calculator. And that's basically it. Those are the two examples I ran out of time for. That should help you with ones like, let me see if I can find it real quick. You know, especially, I'm telling you right now, it'll definitely help with ones like, what's it called, 19 through 26 or whatever. And a couple of them are about a different line also. I'm looking at number, like 17 or 15, something like that. So try those tonight, and let me know if you have any questions, and I'll help you out. Okay? All right, I'll see you later. Bye.